Let's discuss how to determine the hybridization of a certain atom in a Lewis structure. Let's look at this first Lewis structure on the left here. And this leftmost carbon we see has 4 bonds to it. And we could also observe it has 0 lone pairs. So it has 4 electron groups around it. And that gives us Sp3 hybridization. 1s, 3 p orbitals mixed together to make 4 Sp3 hybrid orbitals. And the same can be said for any atom that has 4 bonds, 0 lone pairs, or some combination of bonds and lone pairs that add up to 4. We call them electron groups, and when we get to VSEPR theory in the next module, we'll see how those 4 electron groups help us decide the shape of the molecule. So this carbon, this nitrogen, and that carbon are all Sp3 hybridized. And the nitrogen, of course, has 3 bonds, 1 lone pair, and of course 3 plus 1 is 4, and that gives us Sp3 hybridization. We don't consider the hybridization of the hydrogens because they are using a single 1s orbital to form their CH or NH bonds, and so we don't care about their hybridization. Let's move on to this second molecule now that has a CO double bond in it. Not drawn very clearly, but I'll try to make it a little more clear. And let's look at this carbon here. We see that it has really 3 bonds to it. It has the double bond and 2 single bonds. So it has 3 bonds. In this case, the double bond counts as one type of bond. And it has no lone pairs. And so that adds up to 3. So we have Sp2 type hybridization, where we need 3 equivalent orbitals. And so we take an s and 2 p orbitals, and we mix them together to get 3 equivalent Sp3 hybrid orbitals. And I like to remember that 3 equivalent Sp2 hybrid orbitals. And there's always that leftover p, because of course carbon has 3 2p orbitals. If we use 2 of them to make our Sp2 hybrids, we have 1 p orbital left over, and that's how we get this double bond to O. We can also consider the hybridization of the oxygen. The oxygen has 2 lone pairs, 1 double bond, and it also adds up to 3. And so the oxygen is also Sp2 plus p hybridized. If you want to forget the plus p, that's fine. I just like to keep it there to remind me that there is an additional unhybridized p orbital present. And that's how the oxygen forms its double bond with carbon. It's these 2 p orbitals that are creating that double bond. What about the chlorine? Here we have 2 chlorines on this molecule, and the chlorine has 3 lone pairs and 1 bond. And you can probably already tell me that chlorine is Sp3 hybridized. It has 4 equivalent Sp3 orbitals. And so again, we see 1 lone pair, 2 lone pairs, 3 lone pairs, and the bond, 4 electron groups around that atom, Sp3 hybridization. The carbons in this molecule with the oxygen in the middle are also Sp3 hybridized. How about the O? 2 lone pairs, 2 bonds. I'm sure you're there already. 4 total electron groups means that O is Sp3 hybridized. It has 4 equivalent Sp3 orbitals. And lastly, let's look at this alkene and alkyne structure here and here. For the alkene, those carbons have 3 bonds, no lone pairs. Just like we saw with the carbon in the central carbon here, both of those carbons are Sp2 hybridized. And again, that's Sp2 plus p. If we look at the alkyne is this triple bond here. This carbon has 2 bonds. It doesn't matter that one of them is a triple bond, one of them is a single bond. It simply has 2 bonds, and so that leads to simply sp hybridization. We only need two equivalent bonds, so we take one s and one of the two p orbitals, mix them together, and we get sp hybridization. And I sometimes relate sp hybridization as sp plus p plus p, just to remind myself that there are two unhybridized p orbitals present on this carbon. And we're talking about this carbon right here. Same thing could be said for the other carbon in that triple bond. It is also sp. And these other two p orbitals, as you'll learn about, are used to create the two additional bonds in this triple bond. We form the single bond with one of the sp orbitals, and the two p orbitals on each carbon are aligned parallel to each other, and they form the two additional bonds to bring us to this triple bond formation.